just act normal. Okay, all right, so last time we were talking about dissociation, which is only really for inorganic stuff. So if I plop some salt in, I don't need to show the animation again, do I? You remember doing that? Okay, so they put the little teaspoon of salt in, okay, and basically water hydration shells end up surrounding these things. Okay, so the positive gets attracted to the negative side of water, whereas the negative gets attracted to the positive side of water. And I'm not drawing it that great. But you create these hydration shells, and that is what we call dissolving, which I think is a pretty cool idea. So now I can't see these ions, all I can see is water. Well, how that relates to pH is gets into these different terms. So kind of take a step at a time, and if you guys have questions, just make sure you shout them out. So how inorganic compounds dissociate, and when you see that word split, okay, so how they split determines their effect on pH, which is a measure of how acidic something is. All right, so let's look at the acids first. The reason we call them acids is they release H+ ions whenever they dissociate. So pretty much anything that has an H at the beginning of the formula is going to be an acid. Famous acids. What's that one called? Hydrochloric. You should already have some of these memorized, but if not. Okay, so there's hydrochloric. What's that one? H2SO4. What's S?
Is that sulfur?
Sulfur. All right, so think of a...
Hydro.
Yeah, I know. Savannah's trying to come up with this. The dihydrogen sulfate, but we usually don't call it that. We call it sulfuric acid. Maybe you've heard of that one. Sulfuric acid. Maybe we don't know them.
I don't remember them.
Nitric acid. See, these are all really strong, powerful acids. I would say these two, hydrochloric, HCl, H2SO4, sulfuric, those are probably the two that you're going to mostly deal with in chemistry context. All right, so here's the idea. Let's keep it real simple. If I pour some hydrochloric into water, this is going to split into the cation and the anion. Voila, I have an acid. It's that simple. Okay. So if it releases H+, that's an acid definition. Now here's where it gets really interesting, I think, because it doesn't stay H+ for very long. So if I've got hydrochloric, it dissociates into this and this. Well, floating around out here, I have a water, let's say I've got some water molecules. Okay, there's my Mickey Mouse molecule. Okay. Now the water is polar, so this side of water is negative, this side of water is positive. Now all of a sudden, I've got something positive. And what we're going to find is this gets attracted to this. I've got a positive something, a negative something, and it can attach. I'm going to make it a different color. It can attach right there. And what we've just created is H3O. but this had a positive charge. This whole thing was neutral, other than these kind of slight polar charges. So I've just added an extra positive. So this is slightly positively charged. This thing, H3O, is called a hydronium. A hydronium ion. Okay. So what's going to happen? See if we can make this connection. What's going to happen to the amount of this as I put more acid into water? It's going to, oh, wait a minute. Say again, say again.
Or it's going to become more acidic.
It is. Okay, so as I add more of this, I'm going to have more of this. The more of this, the more of this. It's kind of a domino effect, okay? Now what we say pH is a measure of this. Okay. We're all right so far? All right. It's going to start getting a little bit crazy. All right. Well, let's look at this one. So that's what acids do. Acids increase the hydronium concentration. That's what I put over here. H3O is the hydronium. What we talk about. Well, bases, when they dissociate, they're going to release a different ion, OH negative, which is called a hydroxide ion. Okay. So we'll take a look at one of those. If I zoom, where did I put it? There. Okay, so let's say I've got some of this. How do I know that's going to be a base? Ah, good job. It's going to split. Here's my cation. There's my anion. It's called a polyatomic ion. It's got more than one atom. Okay, so I've got a hydroxide ion, and look at what this is going to do. I've got my little hydronium conglomeration over here. I've got something positive right there. I've got something negative. What's it going to do? Make a prediction. I've got something positive. I've got something negative.
Repel or cancel each other out.
Ooh, yeah. Only they would cancel each other out if they somehow connected. No, I probably didn't do this right. Ding! Okay. Well, why could it do that? Well, because the only thing holding this to this is this little positive, little negative attraction. It's not like this. I can't just rip off one of these ears. Okay, it's covalently held together. They're sharing a pair of electrons. They want to be together. The only thing holding this on is just a mild attraction. Okay, you've met a guy, blind date. You kind of like him, but oh man, that guy's hot. I'm gonna go check that out. Well, it's kind of the same deal. There's a little weak attraction. It's like, I'll kind of hang with you for a while, but I really don't like you that much. All right. Well, then I then find my friends over here. If I can find it again, I screwed it up. Well, I'm gonna hang with you for a little while, but then I really know that person. I'd much rather be with them. Okay. So they can rip that away. So what's going to happen to this value?
It's going to go down.
It's going to go down, okay? And it's going to go down pretty quickly. And what we're just creating, HOH, is water. Okay, so when I add bases to things, what's going to actually happen is I'm going to decrease these values and increase this. Okay. So that's the definition of a base. a base is going to lower the amount of this. Acids are going to raise this value. Maybe I need to reorient my board. No, it's not going to let me do it. Okay. Well, let's look at the one that doesn't really fit any picture. The salts. And most of us think of sodium chloride, which is a salt. It's not the only salt, but it is a salt. Salts, if I look at their formula, they don't have H or OH. So, NaCl, that's a great salt. There's KCl. There's, I just drew a blank. There's magnesium chloride. I don't know why I'm always choosing chloride. There's potassium iodide. All right, there's a whole bunch of other things that aren't acids or bases that would not really affect the pH one way or the other. Salts always form when you put an acid and a base together. So for example, if I have HCl and NaOH, I've got a strong acid, I've got a strong base. I put those together, do a little exchange reaction. What am I going to end up with? Flip-flop your cations. What do you think? What kind of salt?
Oh, that I do not know.
Oh, come on. Flip-flop your cations. If those exchanged places, what formulas do I have? I'd have Na replace the H,
Sodium chloride.
sodium chloride, and the H is now over here. HOH, but we usually don't. Yeah, we usually don't write it that way. So H2. Oh my gosh! That's exactly right. All right, so we have an acid, a base. We put it together. We get a salt always from that kind of reaction, and what's left behind is water because the H is going to bond with the OH over here. Now, I think this is a really good animation. Hopefully it works because this really kind of ties everything together. Okay. Let me see if I can make it a smidge bigger. Oh yeah, there we go. Okay. I don't remember how loud.
In pure water, 1 out of every 500 million water molecules dissociates, forming a hydroxyl ion and a hydrogen ion.
What concentration? 1 in every. Did you catch that?
In pure water, 1 out of every 500 million water molecules dissociates.
500 million. Okay, so I think, I don't remember if Joel was asking about this or Carson, I think.
Probably Joel.
Okay, but they were talking about, does water dissociate on its own? It can. It can, all right? It's odd, 1 in 500 million, and I don't know how someone estimated that one, okay? We're counting. Oh, there it was! And I don't know how they do that. All right, so here's our water. It's going to dissociate on its own. Why shouldn't it? Why is that odd? What's normally holding on to that H? What do you think? Is anything holding on that H?
Well,
Think back to our bonding. What is holding that H on to the O?
very confusing bond.
It is. I mean, it's a covalent bond, so I mean, it'd be like I'm sharing my most treasured item with Chelsea. My most treasured item. I'm going to let you borrow it for a while, but then I know that you're going to give it back to me at some point. So that's going to make us really close friends. Okay? So that's like this. This H is giving its only electron, its most prized possession, to this oxygen, but oxygen's going to give it one of its to borrow too. So it creates this really strong, tight connection, and this hydrogen's doing the same thing. So everybody's valence is full. This seems really odd that for whatever reason, one's going to break away, because that's going to make everybody unhappy. Right? That's like, I'm going to give Chelsea my most prized possession, and she's going to skip town with it. Wow! Right? Everybody's going to be unhappy except Chelsea. But she's going to feel guilty because she left me sad. Okay? So it's really odd, but yeah, it's not very common.
Molecules dissociate.
1 in 500 million. All right, so it's not very common, but it does happen.
Forming a hydroxyl ion and a hydrogen ion. Hydrogen ions quickly associate with other water molecules to form hydronium ions.
Ooh, did you see what happened there? Okay, so I've got this little lone rogue hydrogen ion, which is just a proton. It's lost its only electron. All it is a proton floating around in space. And it's going to be attracted to the negative side of water.
Associate with other water molecules to form hydronium ions. Therefore, in addition to water molecules, pure water contains a low concentration of hydroxyl and hydronium ions.
All right, so what they're saying, translated, in a beaker of water, there is a certain amount, of hydroxyl or hydroxide ions that don't have an extra H, and there's a certain amount of this H3O hydronium ion, naturally. Right? You drink a drink out of the water fountain, you're drinking some hydronium. You're drinking some hydroxide. All right, let's go a little deeper.
The pH scale measures the concentration of hydronium ions in solution. Pure water is considered neutral because it has equal concentrations of hydroxyl and hydronium ions.
Okay, are we good on that? Okay, neutral, when we say pH 7, what we're saying is there's the same amount of this H3O as there is OH negative. Right? That's defined as neutral.
The concentration of hydronium ions in water translates to a neutral pH measurement of 7.
Which is
What happens when an acid, such as hydrochloric acid,
oh man, looks like an army coming down. All right, so I've got a pipette full of hydrochloric acid, HCls, and I'm going to add this to the mix. Make a prediction. What's going to happen?
Become acidic.
Okay, but why?
Because you're adding an acid along with the H plus.
Okay, so what's that HCl going to do as soon as it hits that water?
Connect to on the other one.
Yeah, but what's going to happen to the H and the Cl? They're together right now.
But they're going to split.
They're going to split. What's the fancy word?
Dissociate.
Dissociate, right? They're going to dissociate from each other. They're going to split apart. And as soon as they split apart, all those H's are going to find waters and partner up with them and form those H3Os, the hydroniums. All right, let's see if that's what they show.
HCl is added to
Splits,
water. The
partners.
hydrogen and
Splits,
chloride
partners.
ions dissociate,
Splits, partners.
producing an
Splits,
excess of
partners.
hydrogen ions, and therefore an excess of hydronium ions in solution.
Wow. Is there any regular water left?
No.
I see.
Oh, yeah,
I
one.
see one.
No, I see 2.
Oh, maybe 2. I don't know if that has a partner or not.
No, I think there's 3.
Okay, all right, there's maybe a couple. All right, so basically, as that acid hits the solution, I don't know if you saw what was happening over here. Okay, but my scale started to go toward the acidic side. And that's because I've got lots and lots and lots of these H3Os that have formed. Now, this little H plus is not held on tightly. It's just barely attracted to it. Okay, it's not held on like these two. It's just barely hanging on there. Okay, but that's That's the definition of an acid, is these H pluses are gonna form these H3Os
Hydrogen and chloride ions
until there's no
dissociate,
more water to
producing
bond
an excess
with,
of hydrogen
or it
ions,
runs
and
out of
therefore
H's.
an excess of hydronium ions in solution. Acidic solutions have a pH of less than 7. Each whole number increment in the pH scale reflects a 10-fold difference in hydronium ion concentrations.
Okay, now that's called a log scale. So if I have a pH of 2 versus a pH of 7, it's not a difference of 5. It's actually a difference of 10 to the 5th. Okay, each of these increments, this is a 10-fold change. From here to here, that's a 100-fold change. From here to here, that's a 1,000-fold, a 10,000, a 100,000-fold. So battery acid is 100,000 times more acidic in concentration than pure water. Okay, that's a little bit different than just saying, oh, that's pH 2. That's pH 7. That doesn't sound that dramatic. But there's 100,000 times more hydronium in a pH of 2. Okay, any questions on that? Caitlin, you good?
Mm-hmm.
Savannah, you good?
Yep.
Chelsea? All right.
A solution with a pH of 6 has a 10-fold greater concentration
You guys will
of
be experts,
hydronium
and everybody else
ions than
will
a
be
solution
lost.
with a pH of 7. The most acidic solutions have the lowest pH. Stomach acid, which contains hydrochloric acid, has a pH of 2.
Wow. That's the
When a
strongest
base,
acid.
such as sodium hydroxide, and
Whoop, whoop. Okay. So here we've got a base. How do I know it's a base?
Because that's the OH.
Has the OH on the end. Awesome. All right, so I'm adding this base. It's going to hit the water, and what's it going to do? Ooh, you would think that. You would, I mean, I agree, sort of, Carrie. All right, so the first thing that's going to happen is going to dissociate. Let's see if I can stop it.
AOH.
Oh, all right. So it's going to dissociate first, and I would think that this positive thing is going to get attracted to the negative part of water, but it doesn't, and I don't have a good answer for that. Okay, I'm not exactly sure why it doesn't. I mean, it can. It'll allow it to dissolve, but it's not going to change the pH value. But this is going to do something. It's got an OH negative floating around.
Is added to water, the sodium and hydroxyl ions dissociate. Any hydrogen ions that are released from water are quickly taken up by the hydroxide ions to form water again. A base is a compound that accepts hydrogen ions from water molecules. A basic solution has a very low concentration of hydronium ions and a high pH.
Okay. Now that one's a little bit trickier to see what's going on. So let me back it up a bit. Okay. So the first thing that you should be able to see what happens is
When a
once it
base, such as sodium
dissociates,
hydroxide, NaOH,
once it dissociates, it forms these OH negatives, and then all you see the OH negatives doing is attracting, if you kind of follow this highlighted one, watch what it does. It pulls other H's from other waters. What if, I don't think it'll let me do this, but what if I had an H3O? What would this do? Say it again.
Repel it.
Yeah, well, if I had an extra H here, like if I had had the acid, what's this going to do to that extra H?
Make it stronger.
Okay. I gotta be able to draw it. Okay, so let's say I've got, see if I can get it to work here. All right, so let's imagine, here's our water. Okay. Let me see if I can group all that together. Oh, good, it already is. All right, so then I have an H plus. Let's all grouped together. Okay. So let's say I've got that, and over here someplace I've got a OH. But it's negatively charged. Is that all grouped together? Woohoo! Okay. So here's my water. Let's say I've got an OH3 or 3H3O combination. And I've got this floating around over here. What would it love to have?
That H positive.
Ooh, it would love to have that H positive, because then everybody's happy. So if there's any hydronium in the water, if I add more and more and more base, because this is what the base is going to give off, it's going to steal away these. What's that going to do to my H3O number?
Make it lower.
It's going to really crash it, okay? Because any H3Os that are out there, it's going to steal those away and make water over and over and over and over and over again, okay? So that's what it's showing here. If there was any H3Os, I don't see any in this whole picture. And that's because you've got all these floating around, stealing away that little extra hydrogen, okay? pH value goes way, 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 way to this direction, because now my H3O number is getting smaller and smaller and smaller and smaller. Okay. Questions? There's a lot of information here. Okay. All right, well, let's see if we can kind of put it together. So this pH scale, I don't know who came up with it, but the pH actually stands for potential hydrogen. The potential hydrogen, pH. Okay. So potential hydrogen scale is a measure of the concentration of hydrogen. But the hydrogen usually doesn't last very long in that state. It quickly turns into H3O+. There's not usually just hydrogen floating around in solution. It bonds to water to form that hydronium. And this is the formula. This is actually how we get the pH value. When we say something's got a pH of 7, what we basically have done is we've taken the negative log, which is a math thing, negative log of the hydronium concentration. And this is in moles. Now, if you take, I'm going to give you a page number. Page, I should have had that ready. There's an interesting chart. I wouldn't say it's a really complicated chart, but page 31, if you want to take a look at that, shows you some values. If you look at neutral, the concentration of hydrogen ion is 10 to the negative 7th. And I don't want to get it. Have you guys worked with logs too much other than just hitting the log button on your calculator? Hit it with a log? Okay. Well, when you do the negative log, basically everything's base 10. So if I already have a number base 10, and I take the negative log of something with a negative exponent, it makes it basically all positive. Negative of a negative is a positive. So when you do that, you punch that in your calculator, the calculator is going to spit out at you 7. So all you really have to mentally remember, and keep it real simple, is whatever the exponent is, make it a negative. So if it's already negative, it ends up being positive. Okay? So if I said the concentration of hydronium is 10 to the negative 3, what would be the pH value?
3.
3. Okay, I mean, it sounds maybe more complicated than it really ends up being. Okay. All right. So as my pH changes, it's all based on this concentration of hydronium. Okay. Well, how does this apply really to biology and anatomy? It has really all to do with these. These are really cool, and this is what your worksheet was kind of all about, especially toward the back. If you didn't get to the back yet, this is what it's going to talk about. Buffer systems. When you talk about buffers, and that's what the lab's going to be all about. Buffers are things in the human body. It could also be in nature, but they resist big changes of pH. This all goes back to this principle of homeostasis, keeping things in balance despite external changes. Your entire life, your pH does not fluctuate higher or lower than those values. 7.35, 7.45. Your entire life exists within 1/10 of a pH. If you go below 7.35, you're dead. If you go above 7.45, you're dead. Wow. Okay, so this is a highly regulated system to keep your pH constant. How does it do this? Well, there's two methods. Let's look at this one first. This is what's happening in your blood right now. There is a system. I would write the equation down. We've got H+, which would be given off by an acid. Any acids are going to give that off. In your body, in your blood, you have what's called the bicarbonate ion, HCO3-. Your body creates this from the food that you eat, the bicarbonate ion. When this and this react, it's going to go this direction to form carbonic acid, H2CO3. And since that's an acid, acids always start with an H, or they can give away an H. So, how many of you ate breakfast this morning? Well, nobody! Seriously, nobody ate breakfast.
Mm-hmm.
What would you consider breakfast?
Well, I had an apple.
That's breakfast. Did you eat any food or drink any material other than water? Oh my gosh, you guys need to eat breakfast. You need something.
I like 2 pieces of it.
I can eat breakfast in 5
It makes me
minutes.
sick if I eat breakfast with them.
Really? Bagel, piece of toast, glass of juice. Okay. All right. So I had bowl of cereal and apple cider. I don't know if you guys are apple cider fans, but
Oh, apple cider. Ew, I don't like hot.
delicious. Okay. So glass of apple cider. Is fruit an acid or a base?
Acid.
It's an acid. Almost every fruit is an acid. Citric is always more acid. So when I drank that apple cider, I was ingesting a whole bunch of H+. As soon as it hit my stomach, H+, as it dissociates, okay? That theoretically should drop my pH. My pH should start crashing toward 1s and 2s, okay? But it didn't, because I'm still alive. And here's why. As those H+ entered my blood, they quickly got taken up. They got taken up by this, so it wouldn't connect to water. It never got a chance to connect to water because it got bonded to this, to form this, which is stable. So my pH wouldn't change, okay? And that's what's happening in my blood. In your cells, we have a different system. Again, these are buffer systems, resist change. This one's a little more complicated. Intracellular, so this is within your cells. We've got the hydroxide ion, which is what a base is going to give off. In our cells, we have dihydrogen. I've got 2 hydrogens and a phosphate, dihydrogen phosphate. This is another buffer. If these 2 things react, one of these hydrogens is going to connect to the OH to form water there. What's left behind is 1H PO4 -2. I had a 2 there, but evidently they couldn't understand it. So H2O plus HPO4 -2, which is called monohydrogen phosphate. Okay. So if I ingest, well, hopefully not, but you ingest some strong base, your body's going to be able to deal with that. It's not going to allow it to strip an H plus from someplace else because it's going to give it one here. Okay, so rather than let it react and trash your pH, it's going to give it an H plus from this. It's going to form water, so rather than taking away your hydrogen from something else. Both of these buffers keep your pH very regulated so it doesn't fluctuate one way or the other. Okay. All right, what questions do you guys have? pH. Kayla, any questions? Acids, bases, salts. Why don't salts do any of this?
So they're not getting combined together.
They're not, all right? So when they dissociate, they're not giving an H, they're not going to give an OH, they're not giving anything that's going to affect these equations. Okay? So salts don't affect your
So
pH.
it's like when you sweat, it tastes like, is it like sweating on your face? Do you like taste it, and if it gets in your mouth, it tastes like salt?
I don't know. I mean, the sweat is going to have a very small amount of salt anyway. But yeah, that's not going to really affect our pH one way or the other. Now, a big thing that can is holding our breath or breathing too much. Now, why would that have any effect? This is actually a really interesting one.
What could you breathe?
Okay. Well, we're breathing because why? What's basically the 2 reasons we're breathing? Okay, so we're bringing oxygen in and carbon dioxide out. Okay, so if I'm breathing too much, what's going to happen is my CO2 level, if I'm breathing out too often, my CO2 level is going to get too low. And the problem with that is this guy, carbonic acid. If I look at this formula, somewhere in there, hopefully you see a CO2. Okay. There's extra atoms, but there's CO2 in there. If I'm breathing out too much carbon dioxide, what it's going to start to do is drive this reaction this direction, and that's going to mess up my pH. Same thing as if you hold your breath. If you hold your breath for too long, you can actually make your pH different. Okay. So that's an interesting part. All right, on the back of your worksheet, some of you didn't get that far. I want to give you some time to do that. Hopefully, while you guys are doing that, I'm going to set up some of the equipment, and we might be able to start that a little bit today. At least I'm hoping to. So I would say if you have finished the worksheet front and back, then you can work on your LG packet a little bit. We've gotten a little farther on that now, probably into the D section some. If you haven't finished the worksheet, let's work on that first, the investigating pH part. Okay? All right.